everyone, in today's video we'll be talking about interacting particle states. So let's begin. So in our last videos on interactions in quantum field theory, we talked about the interacting Lagrangian for a scalar field. Before we used a plus, it does not matter if you use a plus or a minus to connect the free term with the interacting term, but in this case we're going to use a minus instead. And just like how there's an interacting Lagrangian, there's also an interacting Hamiltonian. So for the phi-4 interaction that we talked about in the last video, we called this over here the free term, and this part the interaction term. And there's a similar thing for the Hamiltonian. We're going to have a free term and an interaction term, where here is the Hamiltonian interaction term. And it's going to be opposite from the Lagrangian, because think about in cosmic mechanics how the Hamiltonian is PQ dot minus L. So it's a minus L. So if L has like a positive part, it's going to show up as a minus for the Hamiltonian. But for quantum field theory, basically. And we actually solved this interacting field equation by expanding phi in terms of a series, and we developed a perturbative solution, pretty much. And note that the field will now depend on combinations of the creation and annihilation operators, because we're expanding it in terms of the actual free field phi. Well, not necessarily, but it's going to contain products of the free field. And as a result, it's very non-trivial how the interacting field works, because it's going to contain powers of the creation and annihilation operator. And the question now becomes, what does the Hilbert space for an interacting quantum field theory look like? Because before we had AFK and A conjugate K for the free case, and those built and destroyed particles pretty easily. A conjugate K would act on some particle state and give us two particles with some K. And the AFK will act on like this state and give us the vacuum state. It was pretty simple, right? But what happens when we have interactions? Well, we could still use AFK and A conjugate K, nothing's stopping us. But what does AFK and A conjugate K act on? The vacuum state? Well, then what is the vacuum state when we have interactions? Because recall that before we had, like for the free case, the vacuum state would act on the free Hamiltonian and give us 0. And technically you could give us infinity, but basically if you just ignore the infinity term, we get 0. But for interactions, if we use the same state and act on the full Hamiltonian, we're not going to get 0 necessarily, because the full Hamiltonian is going to be a function of the full quantum field, the full interacting quantum field, which contains powers of creation and annihilation operators. So we're not going to get 0 if we, for this part, we're not going to get 0 if we act on the full Hamiltonian with the vacuum state. So basically, defining particle states for an interacting quantum field theory becomes pretty hard to do. And if we want to describe particle interactions, like this one over here, we have two electrons moving towards each other and then repelling each other. This is not a Feynman diagram, by the way. I'm just showing you guys like having two electrons just bouncing off each other, basically. If you want to describe that, we have to use interactions. But how can we even describe these states themselves in an interacting sort of field theory? So that's pretty much the goal of today's video, to develop some sort of interacting particle state theory. Yeah, pretty much that. So let's actually start. So for the free case, we have the free Hamiltonian operator. It acts on the vacuum state and it gives us 0. But for interactions, the full Hamiltonian, which is just the free part plus the interaction part, HI, that's going to act on some new state. Let's call this state omega, and it gives us 0. And we call this the interacting vacuum. And note that omega is not equal to the free vacuum state for the reasons that we described before. Conjugate K acting on this interacting vacuum will not give us a one particle state. So instead, we want to define some sort of analog, some sort of interacting creation operator that acts on omega and gives us some one particle state with momentum k, some one particle interacting state. Let me call that like ki. And then the momentum operator will act on this state and give us an eigenstate of that operator. Okay? And basically, this is kind of bad notation, honestly. This I represents that it's interacting, as in we're using the interacting fields. So again, the goal is to construct some sort of operator that will act on the interacting vacuum state and give us 0. Now, how can we find this operator? Well, to do that, we can use what's called the Klein-Gordon inner product. So we talked about the Klein-Gordon inner product in our video on the Bukov transformation, and we can actually apply it in order to build an interacting creation and annihilation operator. So A of k is the Klein-Gordon inner product between phi and uk, and this phi over here is a free field, right? Now maybe the interacting annihilation operator is the Klein-Gordon inner product between the interacting field and uk. So maybe by replacing the free field of the interacting field in the Klein-Gordon inner product, we can actually have an interacting annihilation operator that will act on the interacting vacuum and give us 0. There are some problems though, because we have the interacting field that we're plugging in here, and the interacting field does not have a very nice form. So what we can do to start playing with free fields is we can just assume, we're going to assume that when t approaches positive or minus infinity, the interacting field actually approaches the form of a free field. So basically, we're assuming that our fields start off interacting in asymptotic times, and then over time, the field takes its interacting form. So like here's like t equals minus infinity, and then the field takes its complicated interacting form, and then becomes a nice free field again when t is plus infinity. And in that way, we are able to plug in the free field expressions into the interacting annihilation operator in order to build particle states. Now, is this assumption actually true? It turns out that it's not true, because a free field will always be a free field. It cannot evolve into an interacting field. And this is something called Hogg's theorem, which we'll talk about in a future video. But basically, we're going to pretend that this theorem does not exist, and we're going to see how far we can go by making this assumption. So with the tools that we've developed, we can actually calculate particle scattering. So we know that in real life, particles interact with each other. For example, take 2 electrons over here. Before the electrons approach each other, and then after the interaction happens, the electrons start receding away from each other. They repel each other, basically. Or just in like classical mechanics, we have like a wall over here. You can throw a basketball at the wall, and the basketball, before it approaches the wall, then after the interaction, the basketball moves away from the wall, because the wall is just a force on the basketball, just like how the electrons exert a force on each other. And basically in quantum field theory, we want to calculate the probability that the electrons pretty much repel each other, and we still have electrons as a result. Because it is possible for electrons to approach each other, and maybe get like a Higgs boson after the interaction, or maybe get like some photons, whatever. You want to find the probability that we just get just electrons out of the process. Now we can represent this with a particle state, where we have one electron with momentum k1 and one electron with momentum k2. And then we have a particle state with one electron with momentum p1. They leave with different momentum p1 and p2. And you want to find the probability that we start off with 2 electrons with these momenta, and then we end out with 2 electrons with different momenta p1 and p2. And to find that probability, we just have to project the final state onto the initial state. This will be the probability amplitude. Note that we're not saying that this state's time evolves to this state. We're saying that this state will time evolve to some general complicated state, which we then measure as this state over here. All right. So how do you find this probability amplitude? Well, we recall that we can represent this state, pretend that electrons don't have any spin. We can write this as A conjugate K1, A conjugate K2, acting on the interacting vacuum state. Because these particles are interacting, so we should use the interacting vacuum. And we call this over here the in state, the incoming particle state. And the outgoing particles, we have momentum P1 and P2. So P1, P2, this is formed by A conjugate P1 acting on A conjugate P2 acting on the interacting vacuum state. And this inner product basically is going to equal, and here we have A's instead of A conjugate K's, because this over here is the same thing as A conjugate P1 acting on the vacuum state conjugated. And we have this conjugated right over here. So basically, to calculate this probability, we just have to find out what this is going to be. This is where we run into some problems, because recall again, we defined A here as the Klein coordinate inner product between U of K and our interacting field, right? And the interacting field is pretty complicated. And we haven't even justified yet if A conjugate P will even act on the interacting vacuum and give us a one particle state with momentum P. We haven't even justified that yet. So what we could do, like we said before, is we can work with asymptotic times. We can assume, basically we're going to assume that A conjugate P acting on the interacting vacuum and the limit as t approaches positive or minus infinity is the exact same thing as the free accretion operator acting on the free vacuum state. Here's the interacting quantum field, and this interacting quantum field is time dependent. So the AFK will also depend on time. Pretty much what we're really saying is that the limit of t approaches plus or minus infinity of AFK of t, which is equal to the limit as t approaches positive or minus infinity of u of k of phi, which again does depend on time, is going to be equal to free annihilation operator, which equals uk with the free field. This is just basically saying that we're assuming that the limit as t approaches positive or minus infinity of our interacting field is our free field. So right now, our expressions for our fields aren't in this product over here. So to get phi into this product, we can just use the formula for the annihilation operator, AFK, and then we can just plug field in that way. The nice thing to note is that AFP of infinity is not equal to AFP of minus infinity, or analogously AFK infinity and AFK minus infinity. And the reason is that due to the fundamental theorem of calculus, the derivative of this over here is equal to this minus this. Then applying that to AFK, this is this minus this, which means that AFK of infinity is this factor plus AFK of minus infinity. So AFK of infinity is not equal to AFK of minus infinity in general, due to this term right over here. So in order for us to actually plug in the field expressions into this product right over here, what we have to do is first find the exact relationship between AFK of infinity and AFK of minus infinity, which requires us to actually evaluate this thing right over here. So partial t of this over here is going to equal to, and we can see that we can just combine these these integrals together to get. And note here that the phi that shows up, this is the interacting field in this case. So we want to find what this is going to be equal to. Well, we can go ahead and actually just move this time derivative in front, giving us. So we can then distribute the time derivative, which will give us this over here. And we can see that some terms already cancel out. This term and this term cancel out. So we get, well, we know that u conjugate k is e to the I k mu x mu, since u of k was defined as minus I k mu x mu. So this means that partial t, the second derivative of t, of this is going to be I k naught times I k naught e to the I k mu x mu, giving us minus k naught e to the I k mu x mu. This is going to be minus e k squared, since k naught equals e, by the way, that's how it's defined. So now we get that. And then we can do that e k squared is just k squared plus m squared, where k is the 3 momentum in this case. So that this is just going to be equal to minus k squared plus m squared e to the I k mu x mu. And then we can do a nice sleight of hand trick. We can write this out as nabla squared plus m squared times e to the I k mu x mu. And we can write this out this way because nabla, again, this is going to be the second spatial derivative. And nabla of e to the I k mu x mu is going to be equal to minus k squared e to the I k mu x mu, because this is e to the I k naught t times e to the minus I k x, where k is the 3 momentum. And the derivative of this is going to give us a factor of minus I k, and then that again will give us the same thing, and this is going to be minus k squared. So we get that. And that's what we had right over here, really. So that's why we can write it out like that. So this means that this over here is going to become this right over here. And now what we can do is we can just factor out the partial derivatives. And that's going to give us equals a k of infinity minus a k minus infinity. And this should have actually been a minus m, by the way, because we distribute this inside, making this be a minus m. And then we just said that nabla squared of e to the I k mu x mu would be like minus k squared e to the I k mu x mu. So this should be like a minus m. So this should have been a minus m. And then when we factor it together, this is going to be a plus m, because this minus would go here, making it a plus. Okay, so factoring it will give us this over here. And then we know that this over here is just how partial mu is defined. So this means that a k of infinity minus a k minus infinity is going to be equal to, and then times phi. We cannot forget the phi that should have been at the end, because we factored the phi out. You guys might wonder, oh, this is going to be 0, right? Since that's the Klein coordinate equation. But no, it's not going to be 0 if our field is interacting, okay? So now we have this equation right over here, which means that a k of infinity is related to the distance a k by the formula. And now we want to plug this formula into here. So, but before we do that, we want to do like a nice like high IQ trick. So right now, this product, we have later times on the left, because infinity is bigger than minus infinity. So later times are on the left. So this product is already time ordered. Okay, time order. And we talked about time ordering in our video on virtual particles. Time ordering of two functions. So say you have like t1 and then t2. It's just going to be phi of t1 t2 if t1 is greater than t2, and then phi of t2, t1 if t2 is greater than t1. So the time ordering of some product, it just puts later times on the right. So since we already had that on the right, we can just go ahead and put in the time ordering operator. So now we can use this formula for the annihilation operator and plug it into this time ordered product for P1 and P2. Note that for P1, you have to label it with P1 over here. And note that we're going to use d to the 4y1 for our spatial integration, what's it called, differential form. I'm going to explain that why we're going to use that letter shortly. But basically, we're going to do the same thing for AP2. AP2 of infinity is going to be I. I'm going to use the spatial derivative of y2, really the space-time derivative, u conjugate p2, and then this thing over here, then phi, and then plus a p2 of minus infinity. All right, and this if p1 of infinity and a p2 of minus infinity, these are not under the integral sign, by the way. They're not being integrated. So also this phi over here is going to be phi of y1, and this phi over here will be phi of y2. So now what we can do is we can just plug those things in. And by plugging them in, we're going to have t of, then I integral of y1. This should be a phi of y2. I'm going to omit that for now, for just clarity's sake. And then multiply by a conjugate k1 of minus infinity, a conjugate k2 of minus infinity, acting on the vacuum state. So why are we doing this? Well, we can see here that by plugging this thing in, now we're gonna have a of p1 of minus infinity and a of p, this should be a of p2 of minus infinity. And what's happening is this is why we chose to use a time ordered product, because now if you actually should be this thing inside, what's going to happen is that this time ordering is going to take the a of p1 of minus infinity and just chuck it to the right, where it's going to annihilate the vacuum, making that term become 0. So by doing this, we're just basically getting rid of all the annihilating terms. So we can do the same thing for a conjugate k. A conjugate of infinity is this over here. We see that we can write in terms of a conjugate k of infinity. This is in the right. So once it's plus infinity, it's going to go to the left and annihilate this covector vacuum. So by doing that, we're going to replace this with of x1, should be k1, x1, and then uk. Note that uk is the conjugated version of u conjugate k. So because this is the conjugated version of this, so they're going to have opposite signs. So uk, and then this spatial, or this whatever this thing is called, x1. I'm going to omit the x1 for now, though. Okay. So basically, I want you guys to picture this in your head. I'm not going to write it explicitly, because it's going to take too long. But try to picture this in your head. We're going to have these operators. We're going to distribute this this vacuum state and this one as well inside. And the terms that contain the annihilation operator by itself and the creation operator by itself, those are going to be time ordered, so they're going to annihilate the vacuum. Meaning, no, we can just ignore all terms with creation and destruction operators, which means that our thing simply just boils down to t, and this is all being multiplied together, right? They're all being multiplied together. So then minus I, these terms, right? Everything here that's not a quantum field can go to the left of the time ordering operator, because time ordering does not affect this at all, because these are already these don't depend explicitly on time, whereas the field does. I mean, technically this plane wave does depend on time, we can just move all the other terms to the front of the time ordering operator, which is going to give us, so we just moved all these things in front, and now I have this expression over here. And now we have the time ordering product of these four quantum fields. And yeah, so what did we just do? Well, we want to find out what this was going to be. And we want to have expressions for our quantum fields inside of here. And then we got this over here. This is what that thing is equal to. And this is pretty big, right? It's pretty hefty. Note that again, u of k is e to the minus I k mu x mu. You might also see written as e to the minus I k x. So if you want to be more like explicit, we could replace this k1 with like e to the minus I k 1 x1. So why are we using x1, x2, y1, y2? Why are we doing that? Well, think about it this way. We used this formula over here, a k1, right? And since we're using a of k1, we should use d to the 4 x1 as well to specify that this is for the first particle, or the particle that we label as the first one. Okay, so if we use k2, we can't like just use some general x. We have to use x2 as well, because this is the integral over the space-time for the second particle. Okay, so, but why do we use the y in y2? We don't have to use y. We're using y for like, just to be like neat, basically. Because think about it this way, we can, because what we considered in this video was what we call 2-to-2 scattering. Two electrons, really like scalar particles. Two scalar particles come in, and two scalar particles come out. We just use the electron as an example of a fake scalar particle, but we could have like things like 10 to 20 scattering, where we have like 10 particles come in, 20 particles come out, each with different momentum, different masses, all like that. And it's going to help us to use x and k to label all the position and momentum data of the first 10 particles, and then y and p to represent all the position and momentum data of the 20 outgoing particles. So we use x and k and y and p just to organize things, so that we know, oh, if it has an x or a k, it represents the incoming particles, y and a p represents the outgoing particles. And we must use different labels for this integration, because we have different particles that we're integrating over, if that makes sense. So yeah, and we actually, and this formula gives us the probability amplitude that two particles come in with momentum k1 and k2, and the same particles leave with momentum p1 and p2. And we can actually generalize this like any n number of particles, like n go in and m go out. Really, it should be m particles go in. The way we've written it, m particles go in and n particles go out. Where you have like, I think it should be like e to the I n plus m, maybe. Here, we call this the LSZ Reduction Formula. It's a formula that relates to the time-ordered product of our interacting quantum fields. These are all interacting fields, by the way. They're not free fields. With the probability amplitude that an m number of particles go in, and then n number of particles go out. So it relates the fields to the probability that some interaction process occurs. And really, we should actually be using the interacting vacuum instead of the free vacuum in this case. Because right now, these are interacting fields. So the interacting field should act on the interacting vacuum. Before we had it as the free vacuum, because before we had it like, oh, we have the asymptotic A of P and A conjugate P, then we could have used the free vacuum. But now we're not using the asymptotic fields anymore. These are actually free fields. So we used asymptotic particle states to start out the derivation, but when we end the derivation, now we're using fields that are not asymptotic. Now we're using the interacting fields, the actual ones that obey the interacting equation. So yeah, so this formula, I know it is very big. it's very, it's a monstrosity. It looks very scary. But I assure you guys that it's not really that bad to use in practice. We can do a lot of things to make this equation a lot less mean, but we have to use a lot of mean machinery to achieve that. So in the next video, we'll be talking about using the interaction picture, which will help us be able to use this equation more efficiently, and then the Gell-Mann theorem, which will help us relate to the what we call the S matrix element to this equation over here. So just to recap, basically, what we were starting out of doing, we were talking about how to build interacting particle states, okay? And we kind of like conjectured that we can use the Klein-Gordon inner product between U of P or U of K and phi to define the interacting annihilation operator, where phi is the interacting field that obeys the interacting field equation. I sometimes, I use the same notation for the interacting field and the free field. This applies for the free field as well, but we can use that to motivate us defining the annihilation operator in terms of the interacting field. Okay, so if you choose this to be interacting, then this will be interacting as well. And basically, we said that A of P will act on the interacting vacuum and hopefully give us one particle with momentum P that satisfies the interacting momentum eigenvalue equation. But we don't actually know if it will do that. So we just assume that it's going to do that in asymptotic times. So we assume it's going to do that at asymptotic times, whereas this will be a free momentum eigenstate. So we assume that's going to do that asymptotic times. And then, based on this, we pretty much have developed, we have built creation and annihilation operators in asymptotic times, so we can consider scattering of particles in asymptotic times. Come in, and then P1 and P2 go out, and then we use this formula to calculate that. And then a P2 at infinity, a conjugate K1 minus infinity, blah, blah, blah. And the reason why we say infinity, infinity, minus infinity, minus infinity is that the incoming part happens at minus infinity, and the outgoing part happens at infinity. And we use infinity minus infinity because we're assuming this equation is true in asymptotic times. Spoiler, it's not actually true, but it's close enough to being true that we can use it in practice. So, yeah, pretty much that. And then we want to introduce our interacting field into this expression, and we use the Klein-Gordon inner product to do that. Formula over here called the LSZ Reduction Formula, relating the what we call the time-ordered endpoint correlation functions. The fancy way of saying the endpoint correlation functions, sandwiched between the vacuum expectation value. Really, actually, we can just like, we could actually just like put it right over here. You know, like just like right over here. Because none of the terms here will like act or annihilate the vacuum. So we can just like move it right in front of here. And basically, to calculate this probability amplitude, we have to calculate this guy right over here. Yeah, that's pretty much how you do it. And in the next video, we're going to talk about how to make this equation less ugly. So I'll see you guys then. Thanks for watching, and have a, yeah, just bye. Okay, bye.